Hello everyone. Today I'm going to be talking to you about holes in the whole argument, substantivalism and symmetries. With broad brushstrokes, substantivalists believe that spacetime points exist. Are substantivalists committed to radical indeterminism? Earman and Norton famously say yes. Most people say no. In this talk, I wish to carve out a path between these naive and sophisticated substantivalist positions. I argue instead for learned substantivalism. On this basis, I defend a novel account of symmetries in physical theories. In section 1, I distinguish three ways, the naive, the learned, and the sophisticated, in which substantivalists might interpret observationally indistinguishable models of a given spacetime theory. Drawing on Balliol's 2018, I argue for the learned way by appeal to physics practice. In section 2, I argue that learned substantivalists are immune to the best recent challenge to substantivalism, namely Earman and Norton's whole argument. In section 3, I disambiguate two classes of symmetries, each with a distinct role in the interpretation of physical theories. Non-physical symmetries, which preserve all physical quantities, are associated with a theory's representational redundancies. Physical symmetries, which preserve only certain physical quantities, are associated with a theory's conservation laws. I show that learned substantivalism offers a new specification of each class. Since substantivalist commitments become a little unclear in non-classical or non-spacetime theories, the purview of my discussion comprehends primarily classical spacetime theories. In this talk, I adopt the semantic conception of scientific theories, which associates a theory with a class of models. For a given theory, the most general class of associated models is the space K of kinematically possible, which consists in tuples of specified geometrical objects. In general relativity, for example, K consists in triples mg phi, as you can see. Given K, the subspace D of dynamically possible models, DPMs, comprises those KPMs whose geometrical objects obey certain dynamical equations, such as Einstein's field equations in general relativity. Moreover, let's suppose realism, so scientific theories are to be interpreted more or less literally, in the sense that we should believe in the existence of entities referred to or quantified over by our best scientific theories. One of our best theories is general relativity, which refers to or quantifies over spacetime points. It therefore seems that realists should be substantivalists. To pick out the ontological content of a given theory T, let's construct an interpretation map from the space of models to the space of possible worlds P. Models are physically equivalent when they correspond to the same possible world. Otherwise, models are physically distinct. And since KPMs which disagree on the dynamical laws are presumably physically distinct, I restrict my attention to constructing an interpretation map from D to P. The most literal interpretation of T construes each DPM as physically distinct. In what follows, I will defend a somewhat less literal interpretation map. The interpretation of a given theory seems to involve two phases. To make matters concrete, suppose that we're dealing with our best spacetime theory, namely general relativity, on some manifold M. In the first phase, we assume that general relativity is empirically adequate, namely, in Colton's words, that the theory makes true claims about the observed phenomena, thus imposing a minimal interpretation on the theory. In the second phase, we decide which, if any, models are physically equivalent. Physically equivalent models must agree on their empirical content, i.e. be observationally indistinguishable. So we might in principle see the first phase as partitioning D into classes of candidates for physical equivalence. Of course, in practice, as Maxwell 1962 has pointed out, classes of observationally indistinguishable solutions are always shifting. Fortunately, some solutions seem even in principle observationally indistinguishable, namely those which are related by isometries or four-dimensional distance-preserving maps on the manifold. We might call isometric solutions qualitatively identical, a la Lewis 1983 and Butterfield 1989. So the second phase asks, when, if ever, are isometric general relativity models physically equivalent? There seem to be three main ways to answer this question for substantivalists, which I array on a scale of decreasing literality of interpretation. I will defend a view of intermediate literality, namely the learned view. To begin with, on the naive view, phi relates physically equivalent models if and only if phi is the identity on M. This is the most literal interpretation of models on which there's an injective mapping from models to possible worlds. However, two immediate problems undermine the naive view. Section 2 examines a third. Firstly, just as physicists standardly interpret potential shifted solutions in electrostatics as corresponding to the same physical state of affairs. So in general relativity, they often interpret diffeomorphic and thus isometric models as physically equivalent. Secondly, the naive view seems undermotivated, at least by realist commitments. The reason for this is that the best justification for realism appears to be some form of no miracles argument, that the best explanation for the novel predictive success of at least some of mature scientific theories is that these theories are correct about the existence of at least some of the entities to which they refer. However, the predictive success which drives the no miracles argument seems primarily about observational or qualitative differences between models. Thus, it's prima facie unclear why a realist should seek the maximally literal interpretation of a theory. The foregoing considerations might initially suggest that substantivalists are only motivated to interpret models literally up to observational or qualitative identity. Thus, on the sophisticated view, phi relates physically equivalent models if and only if phi is an isometry. Indeed, as we've seen, physicists often treat isometric solutions of general relativity as physically equivalent. However, they seem to adopt a more restrictive notion of physical equivalence when considering solutions which are asymptotically flat. For example, when discussing the Hamiltonian formulation of asymptotically flat GR models, Wald adopts this more restrictive notion of physical equivalence. So how does this more restrictive notion generally play out? Consider solutions of general relativity which are asymptotically flat at spatial infinity. One way to understand asymptotic flatness involves taking the manifold to be equipped with a non-physical flat background metric. Then we solve Einstein's field equations subject to the boundary condition that, at spatial infinity in any direction, the metric G is arbitrarily similar to eta, this flat background metric, over sufficiently small regions. The precise details vary among physicist treatments, but on the congenial approach taken by Ashtekar and others in 1991, solutions are physically equivalent if and only if, relative to this background metric, points related by the isometry that relates the two models, become arbitrarily close as one goes towards infinity in any spatial direction. This suggests a novel interpretation of physical theories, intermediate between the naive and the sophisticated views on the scale of decreasing literality. Let's call this the learned view, on which phi relates physically equivalent models if and only if phi is an isometry and phi asymptotically approaches the identity map at spatial infinity. So why exactly should we endorse the learned view rather than the sophisticated view? I wish to suggest 4 reasons. Firstly, there's a conceptual one. To obtain well-defined notions of conserved mass energy and general relativity, and to derive certain important results, then it appears necessary to impose asymptotically flat boundary conditions. But only learned substantivalists can save the prized connection between such conserved quantities and certain dynamical symmetries. Secondly, if the best way to interpret asymptotically flat solutions is the learned way, then this is the best way to interpret models of our universe too. And this is because our universe seems to be undergoing accelerated expansion, and so has positive cosmological constant, and appears asymptotically like de Sitter spacetime, in which, as for asymptotically flat spacetimes, only the learned view captures the special connection between conserved quantities and dynamical symmetries. A third reason to take seriously the learned view, which Balliol points out, is that under standard approaches to quantizing classical theories, in which classical physical quantities correspond to Hermitian operators on Hilbert space, the quantities that generate gauge symmetries are quantized by operators with 0 as the only member of their spectrum, where its spectrum corresponds to the set of possible values of a quantity's measurement outcomes. So if one counts all isometric models as physically equivalent, this seems to prohibit states with non-zero angular momentum. And fourthly and finally, there's a methodological point in favour of the learned view. As we've seen, recent treatments of GR by physicists seem to support the learned view of the interpretation map. Now, Coulton 2015 suggests that philosophers need not defer to physicists unequivocally in the interpretation of physical theories. Nevertheless, it seems to me that a principle of charity to physics practice, that in the interpretation of such practice, we should interpret the claims made by physicists truly when possible. should motivate realist philosophers of physics to take the learned view seriously, to see how far this interpretive practice may coherently extend. I wish now to show that learned substantivalists escape the best challenge to substantivalism unscathed. So this brings me to section 2. Consider a manifold M foliable into global space-like hypersurfaces, Cauchy surfaces, and define the whole diffeomorphism H such that H acts non-trivially only within some region H to the future of the Cauchy surface sigma. By diffeomorphism invariance, whole diffeomorphic models M1 and M2 exist which agree outside H but differ therein. So now consider the whole argument. Suppose substantivalism. Now, according to Earman and Norton, substantivalism would mean that distinct models literally represent distinct worlds where spacetime points have specified properties. So whole diffeomorphic models, as per Earman and Norton, M1 and M2 represent distinct qualitatively identical worlds, W1 and W2. However, if W1 and W2 are distinct, then they agree on all facts up to time t sigma, but differ on certain facts thereafter, and therefore determinism must be false according to general relativity. We'll come back to this notion of determinism soon. But, say Earman and Norton, determinism should fail for a reason of physics. Observationally inconsequential substantivalist metaphysics should not rule out determinism, so we shouldn't accept C. Instead, substantivalism must be false. In this section, I adumbrate 3 classes of popular replies to the whole argument, ones which bite the bullet or grant C, ones which reject the first premise, ones which reject the second premise. In such a short space, the arguments against these competitors can't be decisive. I hope only to indicate some obstacles to their success. Then I show how learned substantivalists reject P2. So firstly, consider the radical and determinist response. What notion of determinism is at issue in the whole argument? It seems to be full determinism, and many distinguish this from qualitative determinism. Qualitative facts, for my purposes, are those which are preserved under isometries, and qualitative determinism restricts the scope of facts under full determinism to only qualitative ones. Qualitative determinism is purely formal and not threatened by substantivalism, whilst full determinism has an interpretative dimension. Interpretations, as we've seen, can differ on whether qualitatively indistinguishable models are physically equivalent. The sophisticated view, for example, equates qualitative and full determinism. On the naive or learned views, full determinism is strictly stronger. Brighouse and Josh Norton resist the assumption that full determinism should fail for a reason of physics. Indeed, Norton 2019 grants C on the putative basis that physical theories determine only qualitative facts, so realist interpreters should seek to preserve only qualitative determinism. However, as we've seen, non-qualitative differences between possibilities, such as time translations or spatial rotations at infinity, do seem to matter to physicists and realist interpreters alike. So substantivalists, I argue, should not bite the bullet. Could we capitulate then? Could we abandon E1? Must realists be substantivalists? Recall Worrell's argument that the no miracles argument for realism works only for those features of our theories which are indispensable to their success, namely the structures or relations between objects. Therefore, by appeal to Garrock's 1972 Einstein algebra reformulation of general relativity, Earman 1989 believed that realists could eschew ontological commitment to spacetime points, thus evading the whole argument. Unfortunately, as Rynasiewicz 1992 pointed out, the whole argument translates directly into the algebraic formalism. It therefore threatens not only substantivalism, but also the most natural formulation, at least according to Earman 1979, in modern terms, of the traditional alternative to substantivalism, namely relationalism. Accordingly, eschewing substantivalism cannot save realists from the whole argument. Instead, they must seek an interpretation of whole diffeomorphic models which saves determinism. So this brings me to various ways to reject the second premise. The first of these involves combining naive substantivalism with metrical essentialism, namely the view that spacetime points possess their geometrical properties essentially. On the metrical essentialist view, it's impossible that a point could exist in but instantiate different geometrical properties at multiple worlds. So substantivalism does not generate indeterminism. One way to motivate this solution is to note that Earman and Norton use the notion of diffeomorphism in posing their threat, rather than of arbitrary permutations of points, and they thus seem to concede a weak essentialism, namely essentialism about points' topological or differential properties. This is because diffeomorphisms preserve points' topological and differential properties, which, if taken to be accidental, would mean that arbitrary permutations of points produce new possibilities. So Maudlin proposes that substantivalists should take metrical as well as topological and differential properties to be essential. The main problem with metrical essentialism, as we've seen, is that physicists seem to treat at least some non-trivial isometric solutions of general relativity as physically equivalent. And this seems difficult to reconcile with the view that spacetime points possess their metrical properties essentially. A second alternative way for substantivalists to reject P2 is to adopt the sophisticated view. Unlike metrical essentialists, sophisticated substantivalists believe that models related by a whole diffeomorphism form a subset of a class of physically equivalent isometric solutions. This view corresponds to denying the existence of distinct, qualitatively identical worlds, namely, it's anti-hexietistic. Butterfield 1989 also combines the sophisticated view with a qualitative counterpart theory, and one might motivate it by noting, as Weatherall has, that isomorphism is just the standard of identity in mathematics, and isometry the standard of isomorphism for Lorentzian manifolds. However, I've argued that some isometric solutions should be interpreted as physically distinct, namely those which differ by time translation or spatial rotation at infinity. So, as we've seen, Earman and Norton assume a naive substantivalism, namely that distinct models literally represent distinct worlds, which can be combined with metrical essentialism or eschewed in favour of sophisticated substantivalism in order to evade the whole argument. But there's a third way to reject the second premise, namely the learned view, which I have argued is the best way to interpret physical theories, especially general relativity. The advantages of this view relative to the naive or sophisticated views, as we've seen, are manifold. So substantivalists should be learned, which suffices to escape the best challenge to substantivalism. I now wish to show that learned substantivalism generates a new way to understand the roles of symmetries in physical theories. And this brings me to section 3. So in general, a symmetry of an object is a transformation on that object which preserves certain salient features. For example, a symmetry of a square is a rotation around its centre by an integer times pi over 2. But a symmetry of a physical theory is a transformation on the space of kinematically possible models, K, which preserves certain physical quantities, where, drawing on Colton 2015, we can understand a quantity as a function from the space K to some value space V, which is a logical space with a parameterization by, say, the real line. The set of quantities is denoted Q, and once we fix the interpretation map between K and the space of possible worlds, some subset Q phi of Q, the physical quantities, picks out quantities which register physical differences, rather than merely, in Colton's words, the turning of idle wheels in a theory's formalism. Models which agree on all the Q phi are physically equivalent. Assuming that symmetries preserve at least the dynamical equations of a theory, we can define the symmetry of that theory as a bijection on the space of dynamically possible models D, which preserves the value of some physical quantities Q primed out of the Q phi. But what exactly does Q primed comprise? The specification of Q primed is the subject of a rich literature on the definition of symmetries in physical theories. A congenial tripartite distinction drawn by Dasgupta in 2016 exists between formal, ontic, and epistemic notions of symmetries. According to formal definitions, a symmetry preserves some formally specified quantity. On ontic definitions, a symmetry preserves all physical quantities. According to epistemic definitions, a symmetry preserves those physical quantities which register observable differences. The latter two definitions alone contain explicitly interpretative dimensions. Now, each of these putative definitions seeks to capture at least one of the following two important roles which symmetries play in physical theories. Firstly, symmetries are associated with representational redundancies, Secondly, symmetries are associated with conservation laws. I argue that each role corresponds to a distinct notion of symmetry. To see this, recall first that Balliol's 2013 showed that popular formal definitions of symmetries applied in physics are incompatible with the interpretative notion, D2, that solutions of T are symmetry related if and only if they are physically equivalent. To illustrate, energetically equivalent or Hamiltonian symmetry related solutions represent observationally distinguishable situations, since one might have the particle moving back and forth on a line segment and the other might have it executing circular motion. Secondly, note that physicists nevertheless commonly appeal to notions like D2. For example, Z believes that the electromagnetic gauge transformation tells us that two gauge potentials describe the same physical state. Such considerations suggest that there are at least two distinct notions picked out by the term symmetry in physical theories, one formal and one an interpretative notion picked out by D2. Let's call those symmetries which relate physically distinct solutions physical symmetries. Balliol's 5 formal definitions would fall within this class, and ostensibly such symmetries are associated with conservation laws, via, say, Noether's or Scher's theorems. Let's call those symmetries which relate physically equivalent solutions non-physical symmetries. So when does a given bijection on the space of dynamically possible models count as a non-physical or physical symmetry? To answer this interpretative question, we must specify the Q phi. According to the learned view, which I've argued is best, a bijection on D is a non-physical symmetry if and only if it's an isometry trivial at spatial infinity. Other bijections on D, which preserve formally defined features of interest to physicists, are physical symmetries. I wish finally to contrast my proposal with Colton's 2015. His core thesis is that a theory may be given a unique literal interpretation, even for unobservable entities, given the imposition of the right constraints, namely the elimination of distinctions without a difference. To begin with, Colton distinguishes two types of symmetries, just as we've done. By contrast with my account, however, Colton counts models as physically distinct only up to observational indistinguishability, which weds him to the sophisticated view that all isometric models, i.e. observationally indistinguishable models, are physically equivalent. And yet, as we've seen, there are very good reasons why physicists and philosophers should count isometric models as physically distinct when they disagree by time translations or spatial rotations at infinity. Substantivalists should therefore be learned, not sophisticated, and endorse my account of symmetries. In conclusion, I've argued that substantivalists should disambiguate two classes of symmetries in physical theories, demarcated according to the learned view. Non-physical symmetries pick out representational redundancies. Physical symmetries are associated with conservation laws. In section 1, I defended learned substantivalism. In section 2, I showed that learned substantivalists are immune to the whole argument. In section 3, I distinguished the roles which non-physical and physical symmetries play in physical theories, the former preserving all physical quantities, the latter only certain ones. Parquet-Colton 2015, I conclude that learned substantivalism offers the best way to understand the roles of symmetries as they are used in physics. So thank you very much all for listening, and I look forward to your questions.